Hello everyone and welcome to this NSO Developer Day session on Introduction to Optical Use Cases. For most of us, we're very comfortable with NSO provisioning IP services on routers like these Cisco NCS devices. These devices connect to each other using transceivers connected together with optical fibers. And the relative cost of these transceivers compared to the router is going up. And when we start to need to do high capacity and long distance connectivity for these routers, we introduce optical systems like these Cisco NCS boxes. Now, these devices come with more transceivers, and more transceivers means more cost. So what Cisco and others in the industry are doing is working to reduce the number of transceivers required to provide these high capacity and long distance links. And for us in the automation space, as automation specialists, we'll expect to see a greater need to understand what's happening in that optical layer, to manage it, to provision it, and basically help deliver services over this newer, simpler, cheaper architecture. So this session is intended to help you as an automation specialist understand a little bit more about this space, understand what we're doing with some of our customers in this space, and then understand how we can work with NSO and help deliver services across optical networks. So the speakers today is myself. I'm a software and automation practice leader in Cisco's customer experience team, and I'm based in Australia. And also joining me is Krishna Shanmughom. Krishna is a delivery architect working with one of our large service provider customers, and specifically at the moment working with NSO in this space. I think it's important to understand neither Krishna or myself come from a networking or optical background. We've just learned enough to be able to speak to these use cases. Just like most of you may not have a CCIE, but you're still able to automate a service provider or enterprise network with NSO. So knowing enough is enough. So I'm going to give a quick overview of what optical systems look like. And so we'll start with the routers. Now our routers have optics in them, and we call these gray optics because they don't have a specific color. There's nothing special about them. And these optics we connect typically into something called an optical transport network device. And this device takes connections from multiple routers, multiple different consumers, and combines those together into a larger amount of traffic. Those optical transport network devices connect into what's called a transponder. Now, the transponder takes essentially white light that is with all different colors, and makes it one specific color. And this is all aligned to standards. There are standards groups that define what are the different colors that we can pick. And all of those colors are spaced just wide enough so that if we put all of those colors down one piece of glass, at the other end, we can pick out all the separate colors. That means we can take our signal and map it onto a color, and we can have 64 or more different colors, each one representing a connection between these optical transport network devices. So the transponder is converting from gray light to a colored light. We then take all of those different colored lights and we put them into a system called line terminating equipment, where we'll have what's called a multiplexer. The multiplexer basically combines all of those different colors together into one beam of light. And it does this typically using very accurate optical elements. Now, there are some other pieces in the line terminating equipment to make sure that the signals are nice and equivalent and everything is combined together. And then for long haul, and this first part of the example would be a subsea system. Now, when we connect routers together across, say, the Atlantic or the Pacific, we connect into specialist equipment for that. And that's where we have special power management, monitoring, and cable management. And this connects into the subsea cable, which has amplifiers to make sure the signal, when it enters one end, can reach all the way to the other, and vice versa. Now, that's a subsea system. When we have a less distance to cover, but still with a higher capacity. For example, in a major city metro area, we need less of this equipment, and it's a little bit simpler. And typically those are built in rings. So your transponder would put colored light into a ring of these multiplexers, and we're able to send the signal around the ring. And an important element here is providing protection or redundancy. So if one of these links breaks, for example, if the subsea link breaks, that there is an overland terrestrial path, or if you're in a city, if a link between two optical sites breaks, that there is an alternative path around the ring for that traffic to follow. Now, all of this is typically deployed and managed with various different systems. And what we're talking about is how can we orchestrate those? So the first one we need to look at is the optical design and planning. Designing these optical networks comes with some challenges, and I'll cover a couple of those a little bit in the next slide. But the first system is where we plan the network and we understand the capacity requirements, and we pick some of the colors that are going to be used. The second piece is an optical controller. And sometimes this is not standalone, it's combined with other elements. And the optical controller understands the topology, it understands the as-built network as opposed to the as-planned network. And it does a really important function of path computation. We have element management systems or network management systems that sometimes combine that optical controller capability, as well as doing the performance management and alarm management. And then finally, we have typically some sort of analytics and telemetry requirements to improve the performance, to monitor the performance of those optical links. And all of these walk through the standard sort of protocols that you should be familiar with in terms of SNMP for alarms, NetConf-YANG maybe for provisioning modern optical devices. Older ones use a standard called TL1, and some devices also use the latest Google-based GNMI, gRPC standards, especially for things like streaming telemetry. Now, the services that we deliver over these networks, there's a bit of a hierarchy, and the ITU actually define some of this hierarchy. And I'm just going to cover a few little pieces that are kind of common that we hear a lot. And so the first one is an optical transport segment. And this is the link between the multiplexers. And this basically represents the colored light, multiple colors of light traveling together in one piece of optical fiber. The next most important one is an optical channel, which represents an end-to-end connectivity joining multiple transport segments together. And this is often called a wavelength or a color. And so that optical channel would represent one color of light entering the optical network and coming out at the other side. And then using those optical transport network devices, we offer a client service, and typically those are called ODUs, and they have different sizes. So we have ODU 0, 1, 2, 3, and 4, representing different bandwidths, 1.25, 2.5 gig, 10 gig, 40 gig, and 100 gig. And these are the services that typically get supplied over an optical network. Now, I mentioned there are some design and implementation challenges with optical networks that are not really there with IP networks. And the first one is we're working in the real world. Physics here actually plays quite an important part in optical networks. And we have things like noise that's introduced by amplifiers. There are limits inside the optical add-drop multiplexers, these multiplexer devices, because they're made with physical components. There are only certain paths that the light can take through them. And then the design to provisioning cycle, unlike an IP device, which may be weeks or a couple of months, in some of these long-haul optical networks, it can actually be over a year between the design of a site and the actual implementation of that whole network and the sites in the network. In terms of provisioning and activation, one thing we can't ignore is safety. Now, with a traditional IP device, the power of the lasers is quite low. And obviously no one's looking into the lasers being fired out of a router. But if you accidentally shone that on something, it's not a problem. But in these optical systems, the power of those lasers is quite high. So we have lots of additional steps in provisioning to make sure that actually everything's plugged in, that there's no stray fibers. We're not going to fire high power laser out of a fiber that's not connected. So those safety elements can complicate the provisioning process. Now, one of the key things in planning, you can fire a laser down a piece of light, but you're not actually guaranteed that it's going to reach the other end. Now, the planning tools are designed to help make sure that that's actually correct, and they should tell you, this is feasible, this will work. But the fact that we're in the real world and things aren't manufactured perfectly, the models in our design tool don't necessarily reflect exactly what's in the real world. And so sometimes we can be told this link is feasible and we can carry this much traffic. But then when it's provisioned, we find that actually it's not capable of doing what we thought it was. And then one of the other last challenges is provisioning performance. Optical systems have a much longer life cycle than an IP device. When they're installed, their operating life may be up to 20 years. So some of the optical systems that are deployed today have quite old processors on the devices. And when we were originally deploying those, no one thought that there would be a need to regularly go and change the configurations dynamically or with automation. So the performance of provisioning of the device can be quite slow. And then the management systems are also the same. When you're talking about a design process and a build process in quarters and years, having the provisioning system take an hour to provision a service wasn't a big deal. But for us in automation, sometimes that can make things more challenging. So with that high level, very quick introduction over, I'd like to hand over to Krishna, who's going to cover in detail some of the use cases that he's implementing with NSO in a tier 1 service provider. So over to you, Krishna.
Thank you very much, Mark, for that wonderful introduction. So I'm going to talk about a transport orchestration case study for a tier 1 service provider based in ANZ. So we have been working with this customer for the last 5 years, helping them with their orchestration journey. And we have already orchestrated around 80 to 90% of their IP network. So as an extension of the current automation journey, the customer wants Cisco to look into their transport network. So their transport network is completely non-Cisco network, which includes Ciena, Infinera, and some other third-party vendors. So we started with the orchestration of their Ciena network. We started with looking into the layer 2 packet services as well as the layer 1 optical. So what you are seeing on the screen is our current service provisioning process. So they got an inventory system in which the operations team go there and design the services. So the transport services are generally more complex than the IP services. So they've got a lot of components which they need to design the inventory system. So once it is designed, the ops team do a civil chair, and then they use the Ciena's element manager system called MCP to provision both the layer 1 optical and the layer 2 packet services. So the provisioning includes entering the service details in MCP, and MCP does some intermediate tasks like finding the best routes between the end and the Z end of the service. And once the user confirms, the service is provisioned. So this is their current process. So the customer wants to use NSO and also the workflow system which we use here from the Bromhorn for the solution. So the orchestration is done based on the once a customer enters the project ID into the IAP, the IAP retrieves the details from the inventory system and then shows all the required elements to the user. Once the validations are all over, then the user can provision the service into NSO, and then NSO provisions it to MCP. So this will be the process. And we are starting in this orchestration with the layer 2 services, and we're already doing the layer 1 as well. So in terms of the NSO architecture for this solution, we are using a LSA based model. So it's a multi-layered model. And we have started with one CFS and one RFS for Ciena network. And the customer wants us to orchestrate the services for Infinera as well. So we have already identified another RFS in the LSA model for Infinera network. So that is the future deployment plan. So in terms of the service modeling patterns for NSO we have used LSA pattern as explained just before. And we already are using MEF aligned patterns using concepts like the virtual circuits, endpoints, and the ports. Why we are specifically using MEF aligned? Because we wanted to use a single service model for both layer 2 and layer 1 services for Ciena, as well as for Infinera in the future as well. So the MEF modeling has got all the required entities which we need for this orchestration. We are using other patterns like the profile patterns. So the profile patterns are used just to have the default values, because all the values required for a service doesn't come from the inventory or from the workflow system. So we use this profile pattern to have all the default values modeled in NSO. We use a service control pattern that is used for versioning in case if you need to use two versions of the same service. Service states are used to identify the state of the service, like reserved, provision, cancelled, etc. UUIDs are used in the service. This is a future requirement for when the service provisioning happens through the digitization layer. UUIDs will be used to identify the services. Then we also use some other functionalities like migration support and also reconciliation of the existing brownfield services. So this slide will give you a high-level overview of how the modeling has done. So from the left, we got two services, the interface CFS and interface RFS. They model the ports or otherwise the A end and Z end of the service. The tunnels are used to model the MPLS TP tunnels. And the virtual connection service is used to model both layer 1 and layer 2 services. And the virtual connection has got an endpoint service as well within. In terms of the challenges or the learnings from this orchestration case study is the optical orchestration is very different to how we traditionally do it in IP network, because the way in which the element manager behaves, the MCP behaves, is by default it is asynchronous in nature. So the service models or the orchestration process needs to take into account this asynchronous nature. And currently, what we are doing in NSO is we got a kicker-based process to identify once the API request is given to MCP, we have to make sure that whether the transaction is successful or not. So, and also MCP, the way in which MCP currently does the provisioning is it does in multi-steps. For example, if we are doing an LSP tunnel provisioning, then in between, once the user enters the end and Z, and then MCP goes and calculates best available routes between the endpoints, and then allows the user to select it. So when we do it through NSO, we don't have the flexibility to find routes in between. So we need to define the best available routes beforehand before we can do the provisioning to MCP. So this we are relying on the path information that is provided by the inventory system and modeled as a route constraint when we do the provisioning to MCP. The other another challenge is MCP has got the capability to find out the changes in the network, and it automatically updates it. For example, like a tunnel goes down or a card is down, it can identify it. But NSO currently means unless NSO does a sync from, NSO cannot actually find it out. So we are actually looking at ways in which we can get a realistic view into NSO from what based on the information provided by MCP. So these are some of the challenges which we have faced and which we are solving. So in terms of timelines, we have already finished the layer 2 packet service provisioning, and we have given deployed it for the UAT testing, and that will be going to production next month. And with respect to the layer 1, we are continuing the development. So with that, I will hand it over to Mark for the closing thoughts. Thank you very much.
Krishna, thanks for that detailed and interesting insight into what we're doing with a tier 1 service provider to help them automate their optical services. I'd just like to quickly cover kind of what is coming next for optical. Now, there are a number of groups that are working on making optical more open, standardizing what's inside the optics, how they interoperate, but also the management of those optics. And so we have the Telecom Infra project led by Facebook and others, Open ROADM, which is helping standardize how optical components interoperate and are managed, and then OpenZR Plus, where the industry is standardizing on laser specifications. Now, all of this is helping with Yang models and API declarations. So an important one is the work being done by the Optical Infrastructure Foundation. And last year, Cisco, along with other vendors, participated in an interoperability event, resulting in advancing the state of management of optical devices. And there's a very interesting report that you can access on their website, and we'll put the link in with the recording information. So when it comes to NSO, talk to us, right? We're familiar with a lot of these use cases. We're not just doing this with Cisco equipment, we're doing optical use cases with third-party equipment as well. NSO has a really fantastic support for third-party devices, and we're adding more and more support into our nets for these optical use cases. And then finally, in the upcoming Cisco Live event, Michael Madden from the NSO engineering team is presenting a breakout session on optical orchestration, where he's going to go into a lot more detail about some of these standard APIs and the work that was done with the OIF. So with that, thank you for your time and attention, and enjoy the rest of Developer Days.